Okay, guys, I'm back at it again with chapter 5, and we're going to finish up with objective number 4 and then move into objective 5. So let me share my screen. Without further ado, get started. We were talking about basic visual pathways last time, and then we were moving on to the receptive field. So what is the receptive field? The receptive field is the portion of the visual field. Remember, the visual field is out here. It's everything we see. Here we've got our right visual field and our left visual field. It's that portion of the visual field in which light affects the activity of a given neuron. So there's a neuron, number 893 here in my visual system, that is affected by light, but it's affected by light only in one particular place in my visual field. So each neuron has a different place that it responds to in the larger visual field. And that is what we call its receptive field. Now, the receptive field can make that neuron either be inhibited or excited, but it's still that one little tiny place out there in the field. So that's the receptive field. And you can learn more from watching this videos here and get a feeling for what that is. The receptive field of a ganglion cell sometimes is very, very small, especially if it responds to color and it's connected to a cone. So when we have those one-on-one connections, so you have the cone connected to one bipolar, connected to one ganglion cell there, we call that a midget ganglion cell. Probably not politically correct at this point, I would think, but they're still putting it in the textbook. Anyway, light is not shining on that cell, but that cell responds to light out here somewhere in the visual field. And it's what happens when a cell, when you have one of those midget ganglion cells, they have very good acuity because it's just a tiny, tiny part of light that responds to them. Okay, I want to talk about a relatively complex concept called lateral inhibition here. You know the terms lateral and inhibition. It just lateral means to the side, it will inhibit. Well, what happens is when a neuron in the visual field becomes active, that will decrease the activity of the surrounding neurons. And this is the ways in which we see borders, right? We can see clear borders. Like you can see the difference between my shoulder and the wall behind me, and you don't think that the wall behind me is part of my shoulder. You don't think that this picture on the wall behind my head is actually part of my head, because we can see those borders very, very clearly. You don't think that my chin is actually connected to my neck, because we're seeing a border there. And so the question is, how do we see these borders so clearly? And we do it by lateral inhibition. So if you think of each one of these squares as a receptive field for a particular neuron, what you'll see here is that light is shining on these areas that are blue or green. So all of those areas light is shining on. Now what's going to happen is when light shines on an area like that, it will tend to inhibit the neurons surrounding it. So you can imagine that this neuron is inhibiting this guy, and this guy, and this guy, and this guy. All of the neurons surrounding it get inhibited when it is excited. Well, what happens is that if you're in the middle of that light, you get inhibited by everyone around you. So you're very inhibited. So those green cells are very, very inhibited. So the cells that respond to those green receptive fields. Whereas the blue is a little bit less inhibited because these cells outside are not active. The white cells are not active. So what happens there is that if we see a square of light like that, we'll tend to see the borders as a little bit brighter than we will the middle. And that helps us, again, to see the borders of an object. So if you look at this, you're going to get an optical illusion there where the intersections there get a little bit gray, and then as you move your eyes, the grayness fades and goes away and comes back. What happens is that these intersections get really flooded from light all around, and that causes an inhibition in the center, and I'll show you that on the next slide. What's happening here is that if you're looking at the center of the intersection, because you've got light shining in the center there, and you've got light from all four sides, what's going to happen is that that receptive area in the center is going to be inhibited very greatly, because, and that's why it starts to appear gray to you, is because it's a little bit more inhibited. Now in the middle of a bar, it's less inhibited because it's only got 2 active cells on each side who are inhibiting it, as opposed to 4 active cells on each side. So what happens is that's why you get those grays there at the intersections. And then again, that helps us to see the borders between one object and another object. Okay, I'm going to talk a little bit about the development of vision in this video, objective number 5. The development of vision, just like everything else, when we talked about the development chapter, you need experience to fine-tune the visual process. Babies are born being able to see, but they don't see very well. So we need that experience to really fine-tune things. And a lot of research has been done with kittens. And when kittens, if you sew one eye shut for 4 to 6 weeks, what you see is that the brain stops responding to that eye at all. Again, it doesn't get the input, doesn't get the neurotropins, doesn't get the apoptosis, it does get the apoptosis, which means those neurons die, or they start responding to something else, if say there's some collateral sprouting or something like that. But a kitten with both eyes shut, you will see if you do it long enough and they don't get any visual experience at all. Now remember, they're not damaging their eyes, they're just sewing their eyelids shut. So once they open them up, the eyes should be fine. But the problem is that the brain is not, because the brain didn't get that visual experience. Now the brain does not respond. And though the eyes are fine once they open them up, I mean, there's no problems with the cornea, with the lens, anything else like that. There is a problem with the brain. The brain needs that input, again, to be able to form. This is, again, why it's so crucial to get children the kinds of varied experiences and don't just sit them in front of a television. So there's a sensitive period for that. If you do it at a certain time, you will get the problems. I want to talk about a couple of other problems that children sometimes have. Children with atypical visual experiences, maybe they don't get the same visual experiences that other children do. And so sometimes children will have what's called a lazy eye, and you can see it there in the picture. If it does persist, you don't get good depth perception, because your ability to see depth depends on both eyes going in the same direction and seeing everything with both eyes. So again, even if you straighten out the eyes after that, the brain is still problematic if you don't do it right away. So with children, we really want to make sure we correct any visual problems right away. And if your child has glasses, make sure they wear those glasses, because we have to correct those problems right away. The astigmatism will cause your eyes to see lines better in one direction than another. But the problem is, if you put up with that and you continue with the astigmatism as a baby, as a young child, your brain will get better at lines in that direction. And then once you correct the astigmatism with glasses, you have the problem of the brain doesn't work right. In cataracts, sometimes you can get them with infants, and that's kind of a clouded vision. You know, again, if they don't get that visual stimulation of the brain is not going to form right. So we definitely want to make sure those cataracts get taken out early in life. Okay, I'm going to discuss the ventral and dorsal streams in the next video. Have a great day.